Good morning, everybody. Today we will be learning about set theory, and this is your first class, and I'll be making a playlist on it, which might contain 2 to 3 videos containing different parts and subparts regarding set theory. First, let us go through the basics itself, and as always, well, not always, but today we'll be starting off again with a limerick and a goal. So the goal today is written over here. To understand sets, get a good start with how it presents information and how it can be used to show mathematical spaces, which we have discussed in relations and functions, the first video, which will be here. Now, we are gonna play with these spaces too and learn more about the relation with sets. But have fun with this short limerick that I have made. A set is a group, that's quite clear. Its elements close, far, or near, with unions and more and intersections galore. It's a theory that mathematicians hold dear. This limerick is actually pretty rhythmic, but it has a lot of deeper meaning into it. And we will be teaching you, well, I will be teaching you regarding what this limerick actually means, and you'll get a much more deep understanding on what unions and intersections are and why mathematicians hold it dear. Let's start with the beginning, shall we? Read it over here. A set is a collection of well-defined objects that share some common property. So, let us just take in consideration that a set is nothing but a collection of well-defined objects. Let's now assume that a set has random bunch of information in it. And when I say information, I mean elements like alphabets, numbers, or some properties that will be mentioned later on. But over here, look at this example. You use curly brackets or set brackets or braces to represent a normal set. This is the roster form, which I'll be talking about in few slides. So over here, A is equal to, in the set brackets, -5, -3, -1, 1, 3, and 5. Simple enough. It contains some information, and well, they do not share much of a common property except for the fact that they are all numbers. But these are not the common properties which we are talking about. We're looking at the more precise questions. How are they related to each other? And we'll soon be connecting this to relations and functions soon enough. But hear me out. This is going to get fun. B is equal to, in braces, 2, 3, 5, 7, 11, 13. So, now look below. We don't have to focus on this much because I'll be teaching you in a few minutes, but we need to know more about discrete sets and continuous sets. And as you can see over here, we use these curly braces for discrete sets, the ones that are used in the definition itself. And we use continuous sets like all these brackets. We use these kinds of brackets for continuous sets. I'll be making this difference later on in the video. Now, first let's talk about what's in the sets itself. The elements, of course. So over here we have the cardinality. So what is the cardinality? It's the number of elements in the set. Simple enough. Over here I have represented it as a space, and what you all should know that a set can be considered or equivalently considered as a space. And when I will introduce you to linear algebra, some parts which you have learned in sets will be also applied to spaces, but with some more well-defined rules. Sets do not follow how spaces work. But for now, as we are going through the basics, I want to visualize everything properly, and so that you can understand the concept more clearly and so that you can become a much more better visual learner. Over here, in space 1, we have the numbers 1, 2, 3, 4, 5, and 6. All the basic numbers. And that's how we'll start off in our next few videos. So, over here, we have in these curly brackets 1, 2, 3, 4, 5, 6. This is showing the relation of how that space and set work together. They are nothing much more than a group, you know. A space and set has only one thing in common, and that they majorly represent a group of or a collection of information. And this is the information we're showing you right now. And the amount of information we're showing you right now is the cardinality, which is the number of elements over here, which is 6. Simple enough. But information cannot just be in one form. Like over here showing you numbers, there's also something as alphabets. A, comma B, comma C, comma D, comma E, comma F, comma G. A set can be as long as you want. It can be till n numbers of elements, and it can be of different types. So we have this classical information with us: a, comma B, comma C, comma D, comma E, comma F, comma G. We can also have negative numbers in it if you want. Or we can also have different, what shall we call, figures, like a spade or a heart or a happy face, and others. But for now, we need to know is that this will be coming in information theory later on, but over here we can represent any kind of information using sets. Well, basically a group of information. That's the basic idea of sets itself. Now, let's learn about the way of writing sets. Now, we have learned about it, but I haven't actually shown you how to represent it. This is where the definition comes in handy, where we have learned that objects share some common property. But I have to still teach you what those common properties are. Now let's talk about the roster form. All elements are listed. As you have seen in previous examples, this is how we write it. This is a roster form. But this is a bit too much dubious to write, and as mathematicians, we all are kinda lazy. So, for example, if I showed you this, I want to give you a challenge and write all the numbers from 1 to infinity and make that list for me or make that set for me, so that whenever I look at it, I know you're writing it from 1 to infinity. Well, you will be writing till 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
3 hours later.
172, 273, 274, 275. This is getting tiring, isn't it? Well, I'll just write it to infinity. But this doesn't make sense, because it's too much to write. But there's an easier way of doing this, and that's by the set builder form. Now, we recognize patterns, and according to it, we generalize it. Generalization in the sense, if we, for example, talk about a small particular group of values and we find a pattern to it that exists in a bigger group, then we just generalize that information, or we make it much more general for that bigger group itself. So that's what generalization is all about, and that's why we mathematicians normally work on n or infinite dimensions, so that we can generalize whatever we know about our environment. So here we have x, where x is less than 6 and where x belongs to n. So as you have seen over here, when we say x is less than n, we are including 1, 2, 3, 4, 5. But you must be wondering, minus 1 is also less than 6, minus 2 is also less than 6, 0 is also less than 6. Why haven't I included them? Over here, I've also mentioned another rule that x also belongs to n, which constrains our set to just natural numbers. So I only include 1, 2, 3, 4, 5. So these two sets actually are explaining the same thing but in two different ways. It's like me being two different persons teaching you different ways of doing a particular solution but giving you the same information. So, what I'm trying to say, you can write an roster form, set builder form. It doesn't matter. You just have to explain how your set works, and that's all. But what you need to know is that set builder form is comparatively much more easier than roster form. Only in cases when you can see any patterns to the set elements itself. And over here, one of them is that all of them are less than 6 and they're in the range of natural numbers. But let's go for a bit more complicated example, shall we? For example, we can go from -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. This is a bit easier compared to my standards, but if you know what the concept is, then this is easier for you. And if you don't know, don't worry, I'm here to help you. Over here, what's the pattern over here? They are integers because we include the negative parts and they have no decimal places. And one more thing is that they're only ranging between -4 and 5. So pause this video and convert it into the set builder form. Now, let us continue. We will write this as x, where x can be all these numbers written in the set. That's what I meant by generalizing. We use a certain variable or a certain amount of information that when given some other constraints, it works as an alternative for the set we have written over here, of the information we have written over here. So x is where x is less than equal to 5, greater than equal to -4. But doesn't that mean I'm also including minus 4 point, minus 3.9, minus 3.2, minus 2.1, or 3.5? Well, yes, but not unless I specify that x belongs to z, where z is a smaller form of saying that of integers. So this covers up this set, gives the same information, but I wrote it in a way so that you can understand it and it's easier for me to explain it to you. So making this video was actually kinda easy, if you see. Now, next we are talking about number lines, 1D spaces. Don't worry, we'll go for 2D spaces also, but let's not get ahead of ourselves. Over here, we are going to be talking about discrete sets and continuous sets. I called it as discrete sets and continuous sets, but nobody else calls it because I'm really special. Now, over here, in discrete sets, we have discrete number of points or discrete amount of information, which means there is no continuous flow of information itself. Over here, in mathematics, we call information as in different forms. Over here, I'm saying it as points. The points in a number line. Okay, let's go for that. Over here, 1, 5, 7, 13, 14, and 20, they're discrete points because they're not having because I haven't marked any other points in between them. I made the continuous chain of lines. I didn't include any real numbers into the situation. So you see, this set is like a normal set, 1, 5, 7, 13, 14, 20. But let's go for continuous sets. Now, when we look at the case of continuous sets, we use curly brackets like these ones over here, which I'm showing with my laser pointer, and we show square brackets Curly brackets are used for these kinds of dots, and close brackets are used for these kinds of dots. And over here, I have some examples to show you how they work. But hear me out. When you see closed brackets or square brackets, or I mean not closed brackets, square brackets, then what you need to know that a square bracket actually represents that you're including something. When you use a curly bracket, it means you're not including something. And I will show you what that means exactly. Now over here you see 5 comma 10. Now you might be feeling weird that okay, only two elements are there. But there are actually infinite amount of elements, and I'll show you how. 5 and 10 are there, but what this brackets actually mean, why I only represented the square brackets and the curly brackets, is that they both represent means it ranges from 5 to 10. It includes all the number between 5 and 10, even the points, even the smaller points. For example, 5.11111111 continuously. It's mind-boggling, but it includes all the numbers into it. And believe me, there are different kinds of infinities, and there is another separate maths for calculating those different kinds of infinities. For example, there are infinite amount of numbers between 5 and 10 because we are looking at those decimal points. Even a small change in decimal point makes a new number or a new information. For example, if I have 5.11111, then if I make a second one, 5.11112, these both are actually different. No matter how much you say they're close, they're actually different numbers representing totally different information. I just added a 0.00001 into 5.11111, and that's how you get a new information. But it actually represents totally different things. And same thing is happening over here. It includes all the numbers, all the real numbers. And by real numbers, I mean literally everything. Natural numbers, whole numbers, rational numbers, irrational numbers. Like, you can't believe it. But these square brackets means that they're including these endpoints. So if I have to make a set, then it would be 5, 5.111111 infinitely, because I told you there are infinite amount of numbers and I can't explain it to you over here in this manner. Nobody can. 2, let's say 9.9999, then 10. So it includes 5 and 10 into the set. If I'm writing it like this. And be careful of the mistake I've done over here, which is that I haven't written in curly brackets. So we can't write all of this, So that's why we represent it in this manner. So understand how we should write sets over here and how we represent information. Now let's look at 5, 17. 5 is close bracketed over here. But when you look at the 17 part, it is open bracketed, which means we're not including 17 in the set itself. So it includes all the numbers between 5 and 17, and it includes 5 but doesn't include 17. So over here, what I'm trying to say is that curved bracket means that it is actually not including the endpoint, while the square bracket means that it actually includes the endpoint. So let's do this together. Look at 5, 17. 5 is included, but 17 isn't, because 17 side has a curved bracket, while 5 side has a square bracket, which actually means that 5 is included, and it will go on to 5 point this, and will go on and reach 16.999, but it wouldn't actually reach 17. So this is the set. Let's do the same case for this 1, 5, where one has the curved bracket and 5 has a square bracket. So 1 has not been included. So it will be 1.1111 goes on till 4.999 comma 5. Last example. 1 isn't included. 17 isn't included. So both of them aren't included, which means we go from 1.111 to somewhere about 16.999. Finished. That's all you need to know. Continuous and discrete, these are the differences. In discrete, they are like random bunch of points and they're not in a continuous chain. While over here, we are considering a continuous chain of real numbers, but the only problem is that because of these curly brackets and square brackets, we have this difference between not including and including the endpoints itself. And I've shown you this example over here, so I hope it's easy for you to understand. Now, let us get back to the best part. Now we're representing set as spaces. Now as you have seen, you can see over here, I made this pictorial diagram for you to understand. So there was an error in the diagram, but as you can see, there is a galaxy over here. This is another galaxy, and this is a bigger galaxy. So I represent all the information in this galaxy to be a bigger group. And over here, the small galaxy over here has a smaller group. So the information contained in this is also information contained in this space, the bigger space. So space 3 has all the information contained in space 2. And this is how I'm showing you this. For example, if 1, 2, 3 and this space information which is in another brackets 1, 2, 3 is given, then this is how we represent it. Same with this case. If 7, 8, 9, 10, 11, 12, 13 it was in the bigger space which is space 3, then over here 2, 3, 4, 5 would also be here in the second space which represents the second space. That information is also contained in space 3 because space 2 is actually inside space 3. And I will come back later to the topic of subsets which will be in my second part of the lecture. But over here, if I'm translating it mathematically, this is what I'm representing you using axes. So there's an x prime axis, y prime axis, and z prime axis, which is like an arbitrary axis over here. So when we are talking about set theory, number theory, linear algebra, then what you need to know that we are not concrete about our math. We, because of playing in higher dimensions, or like Doctor Strange does in higher dimensions, plays with magic. Over here, we are using mathematics to understand those dimensions. But for that, we need to make everything we know about mathematics more abstract, which means anything can be anywhere. Like this can be the origin point, this can be the origin point for this space, this can be the origin point for this space, and we can play with these spaces around. So 3-dimension inside a 3-dimension can happen like this. But in the common sense, this is how it's happening. X prime, y prime, z prime, x, y, z. Space 1 is this bigger space, space 2 is a small space. Space 2 is in space 1. This is what it basically is showing. 1, 2, 3 is one space, and this bigger space, 1, 2, 3 and this space 2 are combined together. And another way of representing is as a group. So these bigger circles over here in these two different examples, this one and this one, these bigger circles are actually space 1s, and these smaller ones are actually space 2s, which means that there are smaller space contained inside it, and they actually have information contained in them. So a set within a set. and that is possible. And we also interpret those sets within Python itself when we're doing programming. And I will also be making more programming classes later on once we understand the basic mathematics and the advanced mathematics. So a set containing set means like a space containing another space. And that's all you need to know. So the connection point, you all need to know set contains information. Set can be considered as a space as long as we have note that the common thing between these two grounds is that they are a group of information, and that we have discrete information and also continuous information that we include in these spaces, and that there are two ways of expressing these spaces itself, or these sets, or these groups, and that's by roster form and set builder form. So I'll repeat myself again. We know what sets are: containing information, same as space only when considered as group. How do we know the elements inside of it? By cardinality, which tells us the number of items inside the set itself, and how we represent it is by roster form, set builder form, and there are different kinds of information stored in these kinds of sets, and that is a discrete information and a continuous information, hence calling them discrete sets and continuous sets respectively. And we also showed you how sets can be considered as spaces when we are only thinking of groups. And what I'm trying to say over here, that sets aren't spaces but are just groups that contain a bunch of information within them. And that's all for the video. Thank you very much. Please like, share, and subscribe by Imperium Engineering. Thank you, see you, and have a great day.